Hello students, this is part 1 of the chapter 5 video. Chapter 5 deals with actually a lot of very kind of different concepts, and so I want to spend a few minutes just kind of outlining what we're covering and where it's being covered and whatnot. So first off, chapter 5 deals with solutions and concentration of solutions, specifically measured in this unit of molarity. We are covering this topic in the conductivity lab, which is being done on campus. So in that lab, am giving the notes for this material, but as always, read it in your book and learn it on your own as well. Solubility is another concept that is being covered in chapter 5. Solubility is addressed in the Ionic Precipitation lab, which is online. And so there's another video in which I go over how to determine whether a compound is soluble or insoluble based on the solubility rules, which is basically a solubility table. Another topic that this chapter deals with is electrolytes versus non-electrolytes. This is another one that is covered in the conductivity lab, which is on campus. So I'm not going to reteach these concepts. Instead, I'm just going to focus on the new material that I haven't taught in other ways. So beyond this material, another major focus of chapter 5 are 5 reaction types that we're going to be learning in this course. These are not the only 5 reaction types that exist on the planet. They're just 5 very common reaction types that chemistry Gen Chem 1 students commonly or usually will be expected to learn about and write equations for and analyze certain things about, each type. So the 5 reaction types that we are going to be learning about in this course are, in no particular order, precipitation reactions, which I cover in great detail on that Ionic Precipitation online lab. So if you want to kind of learn those kind of from the bottom floor up, go ahead and just look at your notes from that lab, the online lab. I will review them really quickly today in just a couple minutes. Precipitation reactions, then acid-base reactions. We'll get into those as well today. Gas evolution reactions. Redox reactions, which I should let you know are also known as oxidation, reduction reactions. This is really more like a nickname. And then combustion reactions. Combustion reactions I actually think were part of a previous chapter. Chapter 3, or I think chapter 3, but we're going to kind of talk about them now. I kind of skipped over them before. So combustion reactions, and let me go ahead and add, this including this concept of combustion analysis, which I will be teaching as well. So these are really all the topics that are covered in chapter 5. So like I said, these top ones are being covered in other places. And so I'm really going to focus this video and part 2 on the 5 reaction types. So like I said, precipitation reactions I teach kind of slower in the online lab video. But let me go quickly through just almost like a practice question on precipitation reactions before we progress into the other ones. So precipitation reactions. So actually, let me do this in the form of a practice question. And like I said, if you haven't already done that online video, maybe just take these notes, understanding that if it's not making sense to you, you might just be a little out of order and need to just complete that lab first and then come back to this. But maybe just from the book readings, you'll be able to follow along anyways. All right, practice question. Let's go ahead and ask this question. If sodium phosphate and nickel 2 chloride are mixed together in aqueous solution meaning that they're both dissolved in water. Will a precipitation reaction occur? And if so, write the complete molecular, complete ionic, and net ionic equations. All right, so in order to do this question, it's essential that you have your solubility table. And like I said, if you want to just go ahead and watch that online lab video so you understand all of this, that may be a good idea. Even if your lab is not yet come, but anyhow. All right, so if sodium phosphate and nickel 2 chloride, so what we want to do is we're asking the question is, when you put these two reactants together and they have an opportunity to exchange ions, to partner swap, will a insoluble precipitate form? So how I always attack these questions is obviously we can't have words, we need symbols. So I think it is wise to write the names of the ions down. So sodium phosphate means that you have the Na plus sodium ion and the phosphate polyatomic ion, PO43 minus, all right? And then nickel 2 chloride, nickel 2 would be the 2+ form of nickel, and chloride being the Cl- anion. All right, so separately, you have two reactants in beakers. And what can happen when you put them in the same beaker? What we are asking is, will any insoluble product form from their partner swapping? So let's go ahead and swap partners so that sodium, let's put him together with the chloride, and let's get the nickel together with the phosphate. All right, so then the question is really, and you can do this, you know, in your mind, or you can just ask it, you know, on paper, what are the two possible products? So obviously sodium chloride is one of them, NaCl, and you do want to address the charges, but since they're equal in magnitude charge, you would just need one of each in the compound. And nickel 2 phosphate. So this product would be Ni. You would need 3 of the nickels for every 2 of the phosphates to get a neutral compound. And so now what you're doing is really the whole, you know, magic happens at this step. Are these aqueous, meaning they're soluble, or are they solid, meaning they're insoluble? So I'll just start with the sodium. When you have your solubility table out, you look for either sodium or chloride, and really you can find either one, but I found sodium first, and it says compounds containing sodium are generally soluble, meaning they're aqueous, and there's no exceptions to that. There's no partner that will nullify that statement. So that is an aqueous compound. How about the nickel? Well, if you look for nickel all the way down, and right, like I said, you always start on the left side of this chart where my finger is. You'll look for nickel, but you're not going to find nickel, but you will find the other one, phosphate. Phosphate is under the heading that says compounds containing these ions are generally insoluble. And just come over here and check and make sure that nickel is not an exception to that rule, and it's not. So therefore, this is an insoluble compound, meaning it is a precipitate, meaning yes, you have a precipitation reaction. So the answer to the first sentence would be yes. After you have identified that it's a precipitation reaction, you can now go ahead and write complete molecular, complete ionic, and net ionic equations. I'm going to need a little bit of room for that. I don't want to forget which one I have here, so let's do complete molecular right here. So the two reactants for sodium phosphate, it's implied that they're aqueous because we said we combine them in aqueous solution. nickel 2 chloride. Okay, so you just basically write the two reactants down. So sodium phosphate and nickel 2 chloride, we're combining those two together. And now you just write down the two products that you identified just a few minutes ago. And the two products were sodium chloride, and he was aqueous. So these are the results of the partner swapping. And nickel 2 phosphate. And we realized that he was solid. At this point, once you get your two reactants down and your two products down, now is the time that you balance the equation. You don't balance it until everybody's in their spots. So just start somewhere by fixing somebody. I see sodium, so I'll write a 3 in front of here to fix the sodium. That gets me 3 chlorines. Now here's where you can kind of see, like, there's 2 chlorines here, so I'm not going to be able to fix this quickly or easily. So I'm just going to instead erase and start with a different species and see if somebody else kind of falls into place a little bit easier. Let me go ahead and do the phosphate. I see 2 phosphates. So I can fix that by doing a 2 right here. That gets me 2 phosphates. That also gets me 6 sodiums. And that I can fix by writing a 6 right here. That gets me 6 chlorines as well. I can get a 3 right there, and that gets me 3 nickels, and that gets me 3 nickels. So that is my balanced complete molecular reaction. Now, or complete molecular equation. Complete ionic equation is all of the aqueous products. And like I said, I go through this a lot slower in the ionic precipitation lab video, so that's why I'm kind of going fast here. All the aqueous products, we want to basically dissociate the compound, really how it really exists in the solution, and represent all the ions as individuals. So this is where, remember earlier when I wrote what the ions were and I had this written down here? Remember how I had this just a few minutes ago at the top of the board, these 4 species? These are the 4 ways that you're going to see them, because those are the individual ions. That's another reason why it's kind of nice to write them down like that. And your job is just to figure out how many of each there are. So there are 6 sodiums. See, there's 6 of him. So I'm going to write it like that. If I have 2 copies of this compound, I have 6 sodiums. I have 2 phosphates. Moving on to this species, I have 3 nickels. So you're basically presenting all the ions as individual species. I have 6 chloride ions. And now I can hit my arrow. I have, on the product side, I have 6 sodiums. I have 6 chlorides. And I'm only doing this to the aqueous species, him, him, and him. Meaning that this precipitate, by the way, this is the precipitate of the reaction. You don't split him up because he does not exist as separate ions. He exists as a compound held together by ionic bonds, you know, a neutral compound. He's not dissociated like the other ones are. If I do it right, everybody should have stayed balanced the whole time. And now I can just see spectator ions. So I see the sodium is a spectator ion. And I see that the chloride is a spectator ion, which means that now I can easily write a net ionic reaction by just taking away the spectator ions. I'm going to reverse this order just so it reads a little bit nicer, although that's not an absolute requirement. And once again, if I did everything correctly, you shouldn't have to be rebalancing it every single time. If it was balanced at the complete molecular, it should just have stayed balanced. And you can see that it does. There's 3 nickels on both sides and 2 phosphates. So the net ionic equation is just literally the formation of the precipitate. All right, that is just a quick review and maybe just an extra practice question on how to identify precipitation reactions. If at the beginning, when we wrote possible products, if both of them had been aqueous and one of them wasn't solid, if both of them had been aqueous, what you would have just said is that no, there's no precipitation reaction. In order to have a precipitation reaction, you have to form a precipitate, which is a solid product. Without that, it is not a precipitation reaction. It really just is no chemical reaction. You're just combining one beaker of free ions, swimming ions, to a different beaker of swimming ions, and they all just swim around together, but you're not really forming anything new. Okay, so that's a quick review of precipitation reactions and solubility tables. Now, moving on to the next type of reaction that we're going to talk about, which is acid-base reactions. So let's go ahead and talk about acid-base reactions. Acid-base reactions have another name, actually. They're also known as neutralization reactions. So we want to be able to be familiar with it. We could really use either term, and we're talking about the same type of reaction. So let's go ahead and first define what an acid-base reaction is. So acid-base reactions occur when an acid is added to a base forming two compounds. Okay, and the two compounds that are always formed are, and we're going to leave that blank for a little bit because we're going to discover it together. All right, so before we can really get into it, so leave that blank for a little bit. Before we can get into it with an example, we actually have to spend a few minutes talking about what in the world is an acid and what in the world is a base. They are the two reactants, because notice the wording. It's when an acid is added to a base. So the acid and the base are the two reactants. And the other two things that we're about to talk about are the two products. By the way, acid-base reactions will always be two reactants, two products. But before we really get into it, we really need to spend some time talking about what's an acid and what's a base. You all have memorized, I don't know, 8 to 10 acids: hydrochloric acid, hydrobromic acid, acetic acid, carbonic acid. You have some in your memory bank. You have some bases in your memory bank: sodium hydroxide, potassium hydroxide, ammonia, ammonium hydroxide, calcium hydroxide. So you've got some examples, but what is an acid? What is a base? So let's go ahead and talk about this for a few minutes. Let me lay this out just a little bit here. There's actually 3 definitions that chemists use to define these terms, acid and base. It's a little bit annoying because you're like, well, why couldn't they just settle on one? Why do they have to use 3 different definitions? And the reality is, it's just that in some contexts, one definition just is easier or works better or is more descriptive or something. Let me just tell you what the 3 definitions are. The first is what are called the Arrhenius definitions. Obviously named after the person who defined them. The second are called the Bronsted-Lowry definitions. And the third are called the Lewis definitions. Both of these will define both, an acid and a base. So here's the issue here. Arrhenius definitions are the ones that we are going to use in Gen Chem 1. In Gen Chem 2, you primarily use the second 2 definitions. And you'll also notice that in your textbook, you learn a little bit about acid and bases in this chapter. And then you learn a whole lot more about acid bases in a later chapter. I can't remember what number it is, but it's in a later chapter. So really, it does come kind of in 2 waves, okay? So we're just on the first wave, which is good because we handle what we should need to handle at this level. So you and I are going to be using the Arrhenius definitions. I'm not even going to tell you what these definitions are. I just want you to know that there's some other ones coming later in chemistry. But we are going to be only talking about the Arrhenius definitions, and these are the only ones that you'll be responsible for. So according to Arrhenius, an acid is a molecular compound, meaning it's made up of nonmetals, okay, one of which is going to be hydrogen, okay. It's a molecular compound that produces H plus, or let me say one or more. Let me write the word hydrogen. Hydrogen cations, which by the way, hydrogen of course is letter H. The hydrogen cation is going to be the same charge as all the other elements in group 1. So when hydrogen makes a cation, he will make the same charge, and that's why they have them over here, by the way, as all of these guys, which now we know is a +1. So hydrogen cation is H+. In aqueous solution. So aqueous solution. So there's a little bit there. First of all, because this definition is only occurring in aqueous solution, anytime you write a acid, you actually automatically know his phase label. You don't have to be told actually. If someone says write the formula for hydrochloric acid, maybe he's reacting in a chemical reaction, his phase label will always be AQ, meaning he's dissolved in water. Because if he's not dissolved in water, he's not going to be the acid. So from here on out, anytime you have an acid, by default, you will always write aqueous as his phase label without exception. Okay, so the whole point of the definition is that you are producing one or more of these H+ ions. So let's ask the question, how? How do you produce it? How does an acid? Well, let's use HCl, probably the most famous acid in the world. How does he produce it? He produces it by dissociating. That's really the method of how he produces it. He falls apart. So the hydrochloric acid molecule, which by the way is a molecular compound, non-metal, breaks. Okay, and he falls apart. And when he falls apart, which means he dissociates, what you get on the other end of that process is you get the H+ ion, which by the way will also be floating around in the water that he was in, okay? And so basically the hydrogen falls off, but the issue is the hydrogen falls off as the cation. So really, well, we'll talk about this. Actually, let me back up for a second here. Let's think about this a little bit for a minute here. H+. Think about H+ for a second with me. The hydrogen atom, can we think about just the hydrogen atom for a minute? Are you all with me that the hydrogen atom has a 1+ nucleus? He has 1 proton. And the hydrogen atom would have 1 electron. Okay? Because atoms would have equal numbers of both, because atoms are neutral. But when he becomes H+, okay, when we're talking about the hydrogen cation, remember, your proton is still there. The protons they don't ever come and go. But essentially what's happened is he's lost his electron. That's why he has a positive charge. So what I'm trying to get you to understand is that the H+ species is just a proton. H+ is a proton. There's nothing else there. It's just a proton. Because, like I said, hydrogen has a proton and an electron. So H+, the electron's gone, it's just the proton. That's why he's a positive charge. He's just a +1 charge. So because of that, when we say produces 1 or more hydrogen cations and we label it H+, you could also say, call this protons. 1 or more protons. So exact same thing. An H plus ion is a proton. So I could have said a molecular compound that produces one or more protons in aqueous solution. Anyhow, you have this molecule. The proton, which is the hydrogen cation, falls off, okay, comes off. And what's left, because what you used to have is a neutral compound, but when you lose a proton, you're going to now have a negative charge. Because you used to be neutral, but you lost one of your positive charges. So whatever's left is going to be negative. This is the dissociation reaction of HCl. And you can see that that's how you produce your H+. So that is what an acid does. Let me grab my eraser. Let's stay on this a little longer. Let's mention this here. Acids, let me do a little bullet point here. Acids can be monoprotic or polyprotic. Okay. Monoprotic or diprotic. Hopefully you can, if you just use your common sense a little bit, you'll know what this means. Mono means one, protic means should make you think of protons. Monoprotics only release one, or only have the capability of releasing one H plus ion, because they only have one H in their name. So examples would be HF, Br. And let me give you one more, and be careful of this here. Acetic acid, HC2H3O2. The reason that this H is listed separately from those H's is that these H's are safely bound to these other atoms. It's only this hydrogen that can be released. So acetic acid is a monoprotic acid. Polyprotic just means more than one. Sometimes you'll hear the word diprotic, which would have been two, but polyprotic is a bigger, more general term. Polyprotic can release more than one H plus ion. So it's just basically acids that have more than one H in them on the front part. Examples would be carbonic acid. He is really a diprotic acid, but he would release two. And a couple other ones that are really famous. Sulfuric can also release two. And phosphoric. Phosphoric acid can release 3 protons. Okay, let's go ahead and write the dissociation for one of those polyprotics, just so we can really think about it. Can we write the dissociation reaction for, let's go carbonic acid. Okay, so carbonic acid, we know his phase label, aqueous. When he releases a proton, these polyprotics always release one at a time. The 2 hydrogens don't fall off at the same time. Okay, that's a really important thing. They don't, the H pluses, they don't just pop. They don't pop off at the same time. One of them comes off in one reaction, and then the second one comes off in a subsequent reaction. So actually, let's look at what happens with the what we call the first dissociation, and then we'll write the second dissociation. So let's take, so basically you had the acid in the intact form. Let's take off the first proton, because it just falls off when it's in the water. Now, if you lose a proton, the way I think about it is you lose the letter H from the formula for sure. The letter H is gone. So now you only have one H, not 2. But you also lose that positive charge. So you used to be overall negative. Sorry, you used to be overall neutral. Now you've lost a positive charge. So on the other end, you'll have that be a negative charge. Okay, so that is, oh, and by the way, all of these are all going to be dissolved in the water, these species. So that's what happens during the first dissociation, but now you still have this molecule. And the hows and whys and all of that are not necessary right now. Let's just kind of see the reaction. Now this molecule can release the second proton. So let's have the second proton fall off. So that H falls off, leaving the rest of the molecule. And you used to be a negative charge, now you've lost another one of your positives, which makes you even more negative than you used to be by 1. So that's CO3 2-. And by the way, this is going to kind of connect these pieces together for you, is that you should recognize these polyatomic ions that are kind of embedded in the acids that you memorize. Of course, that's carbonate, that's the carbonate ion, and that's the bicarbonate ion as well. So monoprotic versus polyprotic acids. We talked about how acids dissociate. Little bit more. Bases will not take nearly as long, don't worry. Let's go ahead and talk just one more kind of, I'm going to call this a little aside. This is just like a little nugget of info about this topic here. That H+ species, which we know is a proton, which is really a free proton. It's like floating around in the water. Will always attach itself to a neighboring water molecule. Because it is floating around in the water and it's so small and so kind of unstable, it's going to want to be conjoined to a water molecule. So let's see how that works. So water, H2O. Let's just draw it like that. We've kind of learned a little bit about how to draw a water molecule. You have this little proton, and he is going to want to get attached to the water molecule. So let's just think about it. Even if we don't, let's not worry right now about how that happens, because it's going to involve bonding and orbitals and all this other stuff that we don't need to know right now. But let's just think of it as this very fundamental level. The new molecule posts, once they kind of meet up, will have 3 hydrogens. You with me on that? And 1 oxygen. And if you combine something that's neutral, because water is a neutral molecule, just like all compounds are neutral, but you've added now a positive charge to it, you get this species right here, H3O+. This species, I would like you to know his name, okay? This species is called, I'm going to run out of room. This species is called the hydronium ion. And what the hydronium ion is the result of that free proton that the acid has released, joining itself or absorbing itself into a water molecule that's nearby, floating around, just minding its own business. And you're going to get this species called H3O+. Becomes a very important species in the second level of chemistry. But the idea here is this. Anytime you have one of these, he really exists as this in reality. But you don't need to care about that. You just will write it as this in your chemical equations. In fact, I'm never even going to have you be writing this in a chemical equation. I want you to know his name. Could you make sure you know his name? That is the hydronium ion, which, by the way, hydro makes you think of water. So, okay, hydration and whatnot. So that is a little bit on what acids do. Oh, no, you know what? We need to say just a little bit more. We need to say a little bit more. Before we get into bases even. This is all stuff on acids. All acids, okay, really can be grouped into 2 categories. I know there's monoprotic and polyprotic. That's one way of looking at it. But another way of looking at this is what we call strong acids versus weak acids. strong acids versus weak acids. So first of all, I want you to make a note here. This distinction has nothing to do with concentration. Concentration being like the molarity, or how much is dissolved in the water. This is a really important distinction because when you hear the word strong, a lot of times people hear strong coffee versus weak coffee. That has to do with concentration. Strong coffee has a lot of solute particles. It's highly concentrated. Weak coffee is very dilute. Okay, like I said, this concept has gone over in the conductivity lab. So if it's new to you, it's okay. We'll get it in another place. But strong versus weak can be used to describe concentration. However, when you're talking about strong versus weak acids or strong versus weak bases, you have to basically be careful that you don't get tempted to think that this is about concentration. It's not. The whole issue about strong acids versus weak acids is this. Strong acids fully dissociate. That means fall apart in water. Okay. Let's use an example of a strong acid. Okay, so as an example, I will tell you that HBr, hydrobromic acid, is a strong acid. And when we say, we just talked about his dissociation, so I'll just put his up on the board here. Or we talked about hydrochlorics. Let me do hydrobromics. When I say fully, because I used to be confused about this when I was a student until, you know, I got it together. What fully means is that 100% of those molecules do this. In other words, if I had a beaker full of 1,000 of these, every one of those, every 1,000 would participate in what we're describing. Every last molecule does it. That's what fully means. It's like 100% participation. So that's what it means to be a strong acid. Every molecule in your beaker will fall apart. And so you're going to get a lot of H+ ions from them, okay? In comparison, weak acids only partially dissociate in water. And as an example, let me go ahead and give you probably the most famous weak acid in the world, which is acetic acid. Whoops. Acetic acid is the acid that's in vinegar, salad dressing and stuff like that. That's acetic acid. It happens to be a weak acid, and I'll talk to you about how to know which is which in just a second. But when we are talking about the fact that he's a weak acid, he does dissociate, otherwise he wouldn't be an acid, but the way that you write it is you write this kind of bi-directional arrow, one going forward and one going reverse. That indicates, that kind of describes that it doesn't happen all the way. Some of it just stays in this form. So you do just write the dissociation reaction kind of as we did before. Take off the hydrogen and then leave the rest of it with a negative charge. But the idea here is that if you had a beaker full of 1,000 of these, only about 1 to 5% of them would actually do this. So let me just write 1 to 5% above. Really, the majority, I guess you could say 95 to 99%, just stay intact. Happy as can be. They don't fully dissociate. But a small percentage of them will fall apart and produce these H+ ions. So this one will produce far fewer of these free protons than the strong acid would have. That's what the difference is between a strong and a weak acid. It's basically how many of them participate in what we're describing. So what was I going to say about this here? Oh, I know. Because of this distinction, this one will produce lots of ions. Are you with me? Lots of them. Because every one of them does this. And because of that, you would call him not only an electrolyte, but a strong electrolyte. In the conductivity lab, we talked about what an electrolyte is. It's basically a compound that will conduct electricity when you put it in water. And the reason it conducts electricity is because it has free charged particles or ions. So this one's going to give you a bunch of them. It's going to be a great electrolyte, lots of ions to conduct electricity. That's why we not only call it an electrolyte, but it's a strong electrolyte. Whereas weak acids, they do produce some ions. So it is an electrolyte, okay, because you need free ions to conduct electricity. But they don't produce nearly as many as something like a strong acid or, frankly, an ionic compound that totally falls apart. So this one gets the distinction of being a weak electrolyte. A weak electrolyte. So hopefully that makes sense. It is an electrolyte. It's just not that great. It will only slightly conduct electricity, but it is an electrolyte. Okay, last thing about strong versus weak, and I know this is a ton, but acids are very important in chemistry, and there's a lot to say about them, but we're almost done, and we're almost coming back to this. How are you supposed to know which ones are strong and which ones are weak? Because you are required to know. I gave you a couple examples because I know, but you are also going to be required to know. Here is the beauty here. When it comes to the strong acid, there are 6 strong acids. It's like a club. There are 6 acids in the universe. Sometimes some textbooks will include a 7th, but we're going to just do the 6 that fit this description, okay? And you have to know them by heart. So most people have a good guess that hydrochloric is strong acid. If you spill hydrochloric acid on yourself, you're not in good shape. And so a lot of people sense that already. So let's add hydrochloric first. How I usually remember this is, you know, there's Cl. So think of hydrochloric first. And then the 2 underneath him are also strong acids. You know, put an H on it and you'll get the acid. So hydrobromic and hydroiodic are the other binary acids, which is 2 atom acids. We talked about binary acids when we talked about how they're named, that are strong. So they're in the club. They're in the strong acid club. The others are nitric acid, very potent, okay? Sulfuric acid and perchloric acid. Those are the 6 strong acids. You want to have that memorized. That's an important distinction. So these are also going to be strong electrolytes, okay? And at the end of the day, all other acids are weak. So it's like a process of elimination. So those are your 6 strong acids, and then all the rest, all other acids are weak, are considered weak acids. And it doesn't matter the concentration. This is about how much they dissociate. So that's your carbonic, phosphoric, acetic acid, but it's also things like lactic acid and ascorbic acid and citric acid, some of your biological acids. Another one that a lot of times people forget, hydrofluoric is weak. Because notice, hydrofluoric was not on your 6 strong acid list. So hydrofluoric is one that sometimes people accidentally put there, but they shouldn't. All other acids are weak, meaning they are weak electrolytes. Okie doke, we have said, I believe, everything that I want to say about acids at this point. Let me just make sure. Okay, a little bit about bases, but bases are not going to take nearly as long. Arrhenius definitions. Back to our Arrhenius definitions. Okay, what is a base? Okay, we talked about what an acid was. What's a base? A base is a compound that produces, so we're back to this producing thing, 1 or more hydroxide ions. And by the way, hydroxide is one of the ones that we have memorized, OH minus, in aqueous solution. So once again, based on that definition, you should know the phase label of all bases. All bases, just go ahead and always assume that they are going to be aqueous. dissolved in water. So the one or more, you've memorized a bunch of bases. So a base that would only produce one would be something like NaOH, sodium hydroxide, or KOH, potassium hydroxide, lithium hydroxide, bases. But they can only produce one because you can see they only have one in their formula. There are some other bases that you memorize that can produce two. Calcium hydroxide, because you can see he has two hydroxides in his chemical formula. Barium hydroxide. Okay, it's a couple examples. So if you have two hydroxides, then you can produce two, in the solution. And it's very similar. How do they produce them? It's exactly what you would assume. It's by dissociating. So that's why they're kind of similar to acids. They kind of fall apart just like acids do. It's just they produce something different. So let's just go ahead and do it for KOH. Let's write the dissociation reaction for KOH. What would he produce when he falls apart? He kind of just dismantles. And really what happens is the front ion falls off and the hydroxide ion remains. So it would leave you a K, and let me just mention the OH minus. Hydroxide, I guess you could say the hydroxide falls off. They separate. What would be left here? Okay, it's the same concept here. If you used to be neutral, and you've lost something, a negative charge, you would be positive, K plus. And really, you're just going to get these metal cations, okay, in the solution as well. So that's how you would write the dissociation of a base. And so bases have this same property of falling apart in the water. Okay. Let's go ahead and just also mention that there is still a strong versus weak concept here. Strong bases versus weak bases. And it is still based on the level of dissociation, but really all we need to focus on for now, because it does get a little bit more reliant on the other definitions, the Bronsted-Lowry and stuff, so I don't want to totally get into it too much here, but I just, at this level, just want you to know examples. Strong bases are any group 1 or group 2 metal hydroxides. Those are always going to be strong bases. So hopefully you know what group 1, group 2 metal hydroxides means. Group 1, group 2 should make you think of the first two columns. So the group 1 metals are your lithium, sodium, potassium metals, and your group 2 metals are your calcium, strontium, barium metals. You put them with a hydroxide, you're going to be a strong base. So for instance, that's a strong base. Weak bases, as examples, I want you to just write down NH3 and NH4OH, which is ammonia and ammonium hydroxide. This, I get that it's hard for you to see how he produces an OH minus. It has a little bit to do with the Bronsted-Lowry definition, so I'm going to just need you to leave that alone for now. I mean, certainly you can look it up, but it has to do with him pulling off a hydrogen off of the water, which then produces the OH minus from the water. So it's not really by dissociation. So leave that alone for now, but just for now, just put these in your bank as weak bases and you really have what you need. Okay, so we got bases, they produce hydroxides, and acids produce the protons, or the H plus ions. Now, let's see if we can wrap this up together here. Acid-base reactions. We started this a little bit ago. It occurs when an acid is added to a base. So let's kind of figure this out kind of real logically. In this beaker, let us put an acid. And we can pick any acid. How about, let's pick hydroiodic acid in this beaker. Now, hydroiodic acid, it is a strong acid. And I'm just picking strong ones just to make it easy on us here. But really, don't worry about the weak part here. Just applicate it the same way, even if it's weak. Just think about the ones that actually do fall apart. So we know it doesn't exist in this intact form. It actually exists as the hydrogen cation that has fallen off and the rest of the molecule with a negative charge. So really, that's what hydroiodic acid actually looks like if you could see it with your eyes. And of course, don't forget, if it's aqueous, that means it's dissolved in water. There are water molecules floating around here by the trillions, okay? But they're just kind of hanging out. They're not really participating in the reaction. They're just watching, okay? So that is our acid beaker. Let's add it to a base. Let's think about what's going on with the base. We can pick any base. How about, let's just go ahead and pick potassium hydroxide. Once again, a base is also dissociating, which means the two species are not together anymore. They're not chemically bound. They're just floating around independently in the water. Okay. Now, when you put them in the same beaker, see, when they're two separate beakers, you're not going to have a chemical reaction. They can't touch. But when you put them in the same beaker, something can happen. So let's think about what we now have in the beaker. And if you write it like me, it'll make for a nice picture here. You've got H+, you've got K+, you've got I-. These are all the different ions that are now floating around in your water, and OH-. So this is very similar to how we analyze precipitation reactions. What you do is you think about what are the possible products. Actually, this time it's not even about possible. You are going to get products, okay? It's not, with precipitation reactions, you have to kind of ask yourself, is one of them going to be a solid? With this, you're guaranteed to get products. So let's think about what the products are going to be. I'm going to carry us through the same thought process. Can the H+ get together with the K+? Can they make a new compound? Will they ever even touch? And the answer is no. They're both positively charged. Will the I- and the hydroxide get together? And no. Negative charges repel each other. They will actually be pushing away from each other the whole time. Will H+ and I- form a new compound? And the answer is no, because if they weren't inclined to chemically bond in this context, they would certainly not in this context. It's just water is the background. So the only new compounds that you have to consider are the result of partner swapping. Partner swapping is the ticket, or double replacement is the ticket, is kind of how you're going to think about the new compounds. So what would they be? Well, in either order, remember, cations always written first. This would give you Ki, which is potassium iodide. And H and OH hopefully you can see when this comes together, it's going to form a neutral compound called water. Okay, and that's H2O. Don't write HOH. H2O is how scientists write it. And how it bonds together, don't worry about that right now. Just understand H and OH gets you H2O, and a positive and a negative charge gets you neutral. That's why you don't have any charge written up here anymore. Okay, and then lastly, phase labels. Water, okay, in this context is going to be liquid, the liquid phase label. You're always going to choose liquid for your water. The other one, technically, you really should look at a solubility table. So let's find either potassium or iodine. I found potassium. It says it's generally soluble, and there's no exceptions. So this is aqueous. So there you go. There are the two products from this acid-base reaction. And now let's come back up here and finish our sentence. Acid-base reactions occur when an acid is added to a base, forming two compounds. The first one is going to be water. I'm writing water. If you want, you could write H2O. Just remember, the phase label will always be liquid, and that really does matter. The second one is what we're going to do is write the word a salt, because it depends on what your acid and your base were. We only got Ki, potassium iodide, because these were the acid and the base that we chose. But this is another way of writing the partner swapping. A salt is just going to be an ionic compound. Let me give you a definition of a salt. Technically, it's an ionic compound that's formed during an acid-base reaction. But let me give you kind of another way of thinking about what a salt is. And a salt is a general chemistry term. It doesn't always refer to table salt. It's a general chem term. It's the ionic compound formed from the, I guess you could say, the back of the acid and the front of the base. I mean, that's pretty lame wording for a chemist, but I suppose you could say the anion from the acid and the cation from the base. But that's going to be the ionic compound that is formed. That's called the salt. So you're always going to get water in a salt. And the salt, I will tell you, is almost always aqueous, just like this one was. So now let's leave that up here for a little bit and let's do a couple practice questions. What we want to understand is that, actually, let me erase this here. You can write complete molecular, complete ionic, and net ionic equations for an acid-base reaction. Let us actually go ahead and just do that, and that's probably where we'll finish this video here. The question is, write complete molecular, complete ionic, and net ionic equations for the reaction between, let's pick an acid and a base, because those are the two chemical species. How about for the reaction between nitric acid and calcium hydroxide? All right, so let's start with the complete molecular. Obviously, those are the two reactants. The acid and the base are the reactants. So nitric acid, we need his chemical formula. He is one that we have memorized, but frankly, remember, if it ends in it utilizes the 8 form of the polyatomic ion, so nitrate. So you can see nitrate in there. And then NO3 is minus, which is why there's one H there. So nitric acid, and we know he's aqueous because acids are aqueous, reacts with calcium hydroxide. CaOH2, aqueous. So how I always do this, if it's an acid-base reaction, I immediately just think here. Acid plus base yields water. I don't even think about it yet. I just write water. And then I think about what is the salt going to be. That's the only really part that you have to think about. So conceptually, think about where the water came from. It was a partner swapping. The water came from the H's and the OH's, just like in my 2 beakers. You shouldn't be drawing beakers. That's just for teaching, but that's not for every time, okay? So the waters were generated from the acids H's and the bases OH's. That's what gave you waters. That's what gave you waters. The salt is going to come from the anion here and the cation there. So it's like still a partner swapping. So remember, cations are always written first in your chemical formula. So you really just want to think about what would that compound be? Well, Ca is the 2+ ion. Calcium's in group 2. And nitrate is a 1- anion. So therefore, you would need 2 nitrates for every 1, and I'm going to do an aqueous down there, for every 1 calcium. And that's going to be the compound that would be formed. So you really have to make sure your salt is a neutral compound. You know, you have to represent what the compound actually is. It would be calcium nitrate, which is CaNO3 2. He is aqueous, but I know that based on the fact that anything that contains nitrate is always aqueous with no exceptions. Okay, once you write your species, acid plus base yields water plus salt. I'm going to erase this just to clean it up a little bit. Then don't ever forget, you have to balance your equations. You can never present an unbalanced equation. So only once you have your species in place and they're, the correct formulas, then you balance it. So just, and by the way, these are very easy to balance. 2 nitrates, I see that right away. I can get 2 nitrates by coming over here. 2 nitrates. And now I've got, for acid-base reactions, okay, this is one little technique that can be useful. Let me back up for a minute. I forgot to say this. When you are balancing acid-base reactions, important tip, you balance the salt species first, always. Usually I say start somewhere by fixing someone, not with acid-base reactions. Your eye goes to the salt. You balance him first. And the reason I say that is it's way easier. You're going to see things fall into place easier. So I did it by habit, but that's why I did it. So 2 nitrates, that's why I balanced that first. I put him there. And the 1 calcium, it's already balanced. Then after you're done balancing the salt species, think about, really the only issue is how many waters will you get? It's a different kind of technique for acid-base balancing. How many waters will you get? And come back and just think about it like this. The acid is going to give me 2 hydrogens. See that? He's going to give me 2 hydrogens. The base, because this doesn't have a coefficient, will give me 2 OHs. And if it helps you to write it down, at least while you're still learning it, this can help. So how many waters will that get? 1, 2. Okay. It's a little bit easier to think of it as building the water molecules than it is counting H's, because you're going to have to count H's and counting O's if you do it like the classic way, and it's not really necessary. Think about how to build the waters, and that will make it a little bit easier to balance your acid-base reactions. So this one is now balanced and complete ionic. Once again, just like all complete ionics, you zero in on any of the aqueous species and you present them as dissociated ions, because that's really what they are. An acid has dissociated. So how many H pluses do I get? I actually have 2 because of that coefficient. I will also have 2 nitrate ions. And by the way, notice everybody gets a charge. It's called a complete ionic for a reason. Ions have charges. And everybody gets a phase label. So I handled him. I broke him down. Now let's break him down. 1 calcium 2 plus, aqueous, plus how many hydroxides does this get me? It gets me 2 hydroxide species. So you have to kind of keep those polyatomic ions intact. You understand that's hydroxide. You want to be so familiar with that. That's kind of the polyatomic ion, and he stays together. Now I hit my arrow. Now, this is where it was important that you remember that water is liquid, because I am not breaking him up. He is a neutral compound. He's not a collection of ions. He's a covalently bound molecular compound, and we leave him alone. You only mess with the aqueous species, so just rewrite him. He's kind of like the precipitate. He's not a precipitate. Precipitates would have been solid, but he plays that role in this type of reaction. And just keep on going with this last chemical species, the calcium 2 plus. And how many nitrates? I've got 2 nitrates. Remember, you don't want to represent this like this, because if they're not connected together, this would be the wrong way to say that. They're independent species, and there's 2 of them. They're floating around together. When you use a subscript, you kind of are implying that they're in a compound together. So you don't want to do that. All right? Just as with precipitation reactions, there are spectator ions with these. You can go ahead and identify them. Nitrate is a spectator ion. He's present in the exact same form, left and right of the arrow. And the other one is the calcium, which leaves you a net ionic reaction of everybody left over. 2H plus aqueous plus 2OH minus aqueous yields 2 waters. And that is your net ionic equation. Now, it is fine to leave the 2's in there for this context of net ionic reactions for like acid-base reactions. Technically speaking, if you can reduce a chemical reaction, which means like divide all of them by a factor, usually 2, you should. So it is also fine if you present that net ionic like this. That would also be okay. But if you left the 2's in there, I would accept that fine as well. I want you to make one note to yourself. The net ionic equation for all acid-base reactions is the same. If you do these a few times, you're going to see that you really always end up with that exact same reaction, the formation of water. So as we close out this video, let me give you a practice question for you to try on your own and prove to yourself that that is indeed the case. So let me have you try to write the complete molecular ionic and net ionic equations for the reaction between, how about phosphoric acid and lithium hydroxide? See if you can use the knowledge that we just imparted to do this. This is another acid-base reaction. Acid plus base yields water plus salt. So see if you can do that, and if you can, you have learned something wonderful. So I will see you next time for part 2.